We'll start in 1 minute. In a few minutes, we'll look at the alternating series test in section 11.4. But first, we'll look at some of those series that we saw yesterday that we didn't get to. So we just got started on this one. And so my suggestion was to look at the largest power in the numerator and the largest power in the denominator. So the square root of n to the fifth in the denominator is n to the 5/2. And then simplify this. This becomes 1 over n to the 1/2. So if we use the limit comparison test with 1 over n to the 1/2, we might be able to determine if this series converges or diverges. Okay, so we compute the limit as n approaches infinity of n squared minus 2n plus 5 over the square root of n to the fifth plus 3 divided by 1 over n to the 1/2, which is the 1 over the square root of n. And then simplify a little bit. Okay, so when we simplify in the numerator, we're going to get the quantity n squared minus 2n plus 5 times n to the 1/2. And then in the denominator, it's just the square root of n to the fifth plus 3. Okay, so in the numerator, we get n to the 5/2 because n to the second times n to the 1/2 is n to the 5/2 minus 2n to the 3/2 plus 5n to the 1/2 divided by the square root of n to the fifth plus 3. So in the denominator, the largest power in the denominator is n to the 5/2 because we have the square root of n to the fifth. So if we multiply it by 1 in the form 1 over the square root of n to the fifth divided by 1 over the square root of n to the fifth, or another way to write it is divide the numerator by the square root of n to the fifth. and then divide the denominator by the square root of n to the fifth. So let's see. I guess I'll just divide each term in the numerator, n to the 5/2 minus 2 times n to the 3/2 plus 5n to the 1/2. Divide that all by n to the 5/2. And then in the denominator, we have the square root of n to the 5th plus 3. But here I'm going to multiply that by 1 over the square root of n to the 5th, which is the same thing as 1 over n to the 5/2. Okay, in the numerator, n to the 5/2 divided by n to the 5/2 is 1. And then minus 2 times n to the 3/2 over n to the 5/2 is minus 2 over n. And then plus 5 to the n/2 divided by n to the 5/2 is 5 over n to the 2nd. And then in the denominator, when we multiply these two terms, we're going to get the square root of n to the 5th divided by n to the 5th, which is just 1, and then plus 3 over n to the 5th. Okay, now we can compute the limit. If we let n go to infinity, these two terms in the numerator go to 0. The minus 2 over n plus 5 over n squared, those go to 0. In the denominator, the 3 over n to the 5th goes to 0. So the limit is 1 divided by the square root of 1, or 1. Okay, so according to the limit comparison test, since the limit of the terms from this series and the terms from another series, the p series of 1 over n to the 1/2, since the limit of the ratio equals a positive finite number, that means either both series converge or both diverge. But we know that this series diverges. It's a p series, and the value of p is less than 1. So since we know that this series diverges, then we conclude that this one also diverges by the limit comparison test. Diverges. Okay, in the next example, the series of the terms 5 to the n divided by 4 plus 7 to the n as n ranges from 1 to infinity. Okay, so what are your thoughts on this one? So this is a problem from section 11.4. And we saw two different methods for evaluating infinite series. One is the comparison test, and the other one is the limit comparison test. And oftentimes there's more than one way to determine if an infinite series is convergent or divergent. So I guess the answer I'm trying to get from you is, do you think we should use the comparison test, or should we use the limit comparison test? And if we use one or the other, then what are we going to compare it with? Well, it turns out we can use either. Maybe I'll at least get you started on either way to do it. If we do the comparison test, this is how I would start. I'm thinking that this infinite series should converge because I see 5 to the nth over 7 to the nth, or the fraction 5/7 to the nth, and the series of 5/7 to the nth is a geometric series that converges. So I'm thinking about comparing this to the geometric series where the terms are 5/7 to the nth. Okay, so let's start this way. You'll agree that 7 to the nth plus 4 is greater than 7 to the nth for n greater than or equal to 1. So that's pretty obvious. So if we reciprocate, then 1 over 7 to the nth plus 4 is less than 1 over 7 to the nth. And if I multiply both sides by 5 to the nth, which is just a positive number, the inequality will be preserved. So 5 to the nth over 7 to the nth plus 4 is less than 5 to the nth over 7 to the nth. Okay, so we know that the infinite series, 5 to the nth over 7 to the nth, can be written as the fraction 5/7 to the nth. We know that this converges. It's a geometric series, and the common ratio is between -1 and 1, so it converges. So since that converges, and the terms from this infinite series are less than the terms from the convergent series, this infinite series converges by the comparison test. Okay. Well, if you prefer the limit comparison test, not a problem. Limit comparison test, we'll compare it to the same series. So we compute the limit as n approaches infinity. The terms from the original series, 5 to the n over 4 plus 7 to the n, and then we're dividing it by 5 to the n over 7 to the n. Simplify that ratio of quotients. So this will be 5 to the n over 4 plus 7 to the n times 7 to the n over 5 to the n. Hey, in the numerator, 5 to the n times 7 to the n is equivalent to 35 to the n. And in the denominator, we get 4 times 5 to the n plus 35 to the n. Hey, now what? Well, if we multiply this expression by 1 in the form 1 over 35 to the n divided by 1 over 35 to the n, or equivalently, if you just divide the numerator by 35 to the n and divide the denominator by 35 to the n, so here I'll just say I'm going to multiply the numerator by 1 over 35 to the n and multiply the denominator by 1 over 35 to the n. Then in the numerator, we get 1. In the denominator, we get 4 times 5 to the n over 35 to the n plus 1. And this term goes to 0, so the limit is equal to 1. Since the limit of the ratio is a finite positive number, then by the limit comparison test, the original series converges because we know that the series that we can compare it to converges. Okay, the next one, the infinite series of 1 over n to the n as n ranges from 1 to infinity. Well, we can just use either the limit comparison test or the comparison test. So I'm just going to compare this series of 1 over n to the n with the series 1 over n to the second. So either using the comparison test or the limit comparison test will work, but we compare it with this series 1 over n to the second. So how do we justify comparing it with that? We know that this series converges. It's a p series. The value of p is greater than 1. So this p series converges because p is equal to 2, which is greater than 1. So we need to justify using this as a series to compare it with. So what does that mean we have to do? Yeah, we have to show that the terms from the series 1 over n to the n are less than the terms 1 over n to the second. So we can start by this. We can say n to the nth, is that going to be greater than, possibly equal to n to the second? Well, when n is 1, they're equal. When n is 2, they're equal. But then when n is 3, n to the nth is greater than n to the second. So this is true for n greater than or equal to 1. So that means the reciprocals, we have a reverse inequality. So the reciprocate the left-hand side, 1 over n to the nth is less than or equal to 1 over n to the second. So we're pretty much done. We know that, as I've already stated, this P series converges. And since the terms from the given series are less than or equal to the terms from this convergence series, by the comparison test, this series also converges. Okay, that's all there is to that. Okay, in the next section, 11.5. Oops. So on the cover sheet, I had the wrong section, but we're starting section 5 in chapter 11. Okay, so just a note, one criterion before the integral test, the comparison test, or the limit comparison test can be applied is that the terms of a series are all positive. In this section, we are introduced to alternating series. An alternating series is a series whose terms are alternately positive and negative. Okay, a couple of examples of alternating series. So this one, 1 minus 4 plus 9 minus 16 plus 25 minus 36, and so on. So to get the positive followed by a negative terms, we use negative 1 raised to an exponent involving n. In this one, since n begins with 1 and the first term is positive, we use negative 1 to the exponent n minus 1. And then the other numbers are n to the second. Okay, in this other series, the first term is negative. So it's negative 1 plus 1/2 minus 1/6 plus 1/24, and so on. So this time, we use negative 1 to the n. And you can see when n is 1, negative 1 to the first is negative. And then the other terms are determined by 1 divided by n factorial. Okay, so as you saw in those two examples, if the sequence a sub n is an alternating sequence, then either a sub n is equal to negative 1 to the n minus 1 times b sub n, or a sub n is equal to negative 1 to the n times b sub n, where b sub n is a positive number. And note that b sub n is just the absolute value of a sub n for all n. Okay, the alternating series test. So if the alternating series, where the terms are negative 1 to the n minus 1 times b sub n, that's equal to b sub n, or b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, and so on. where b sub n is greater than 0, if this alternating series satisfies these two conditions, then the series is convergent. So the two conditions, the first one, b sub n plus 1 is less than or equal to b sub n for all n. So this just means, well, if we have strictly less than, it means that the b sub n sequence is decreasing. If the b sub n plus 1 term is less than b sub n, then it's decreasing, or it could possibly be equal to. And then also the second condition is if the limit of the b sub n sequence is equal to 0, if those two conditions are satisfied, then the alternating series is convergent. So I'm just going to draw a picture of what's going on here. If we use S sub n as the sequence of partial sums, then S sub 1 is equal to B sub 1. S sub 2 is B sub 1 minus B sub 2. What's S sub 3? The third term in the sequence of partial sums. Exactly. B sub 1 minus B sub 2 plus B sub 3. And I'll just write one more. S sub 4 is B sub 1 minus B sub 2 plus B sub 3 minus B sub 4. Okay, so if we have a convergent alternating series, then the b sub n sequence is decreasing and its limit is 0. So this is just a drawing of what's going on. So the first term in the sequence of partial sums, S sub 1, that's equal to a positive number, B sub 1. So let's just put it over here somewhere. This is S sub 1 equals B sub 1. And where will S sub 2 be relative to S sub 1? Well, S sub 2 is found by subtracting a number from B sub 1. Remember, B sub 2 by itself is positive, and we're subtracting it from B sub 1, but B sub 2 is smaller than B sub 1. So S sub 2 is going to be to the left of S sub 1, but it won't go all the way to 0 because in general we're subtracting a number smaller than the number that we're subtracting it from. So over here we'll be at S sub 2. Then S sub 3 is S sub 2 plus a positive number. But this number that we're adding, B sub 3, is smaller than the number B sub 2. So S sub 3 will be to the right of S sub 2, but it will be to the left of S sub 1. And then where's S sub 4 relative to the numbers that we plotted?
Left of S sub 2?
Yeah, S sub 4 will be to the left of S sub 3, but it will be to the right of S sub 2, because we're subtracting a number that's smaller than the number that we're subtracting it from. So S sub 4 will be over here, and it will be greater than S sub 2. So if we continue this, I'll just write in a couple of more. S sub 5 will be to the right of S sub 4, but to the left of S sub 3. S sub 6 will be to the right of S sub 4, but to the left of S sub 5, and so on. So the sequence of terms with even subscripts, so if I refer to the sequence of even subscripts as S sub 2 sub n, or S sub 2n, this sequence is increasing and it's bounded above. So this is increasing and bounded above, I can spell, and bounded above. So what does that mean? It's a monotonic sequence that is increasing and bounded above, so that means by the monotonic convergence theorem, it's converging to a finite number. And the sequence of odd terms, S sub 2n minus 1. So what are the sequence of odd terms doing? This sequence is decreasing, and it's bounded below. So it's also a monotonic sequence that is bounded in the direction that it's headed. So it also has a limit. And if you think a little bit more about it, the sequence of even subscripts is bounded above by every term from the sequence with odd subscripts, and vice versa. So anyway, the limit of each of those two sequences turns out to be the same number. Let's just call it S. And so the overall sequence, the sequence of partial sums, S1, S2, S3, S4, S5, S6, and so on, they're approaching the limit S. So the alternating series will converge under those conditions. Okay. So here's a note. The integral test, the comparison test, and limit comparison test tell us when an infinite series converges or diverges. But the alternating series test only tells us when a series converges. So if we see an alternating series, but one or the other of the conditions is not satisfied, we have to use another test to conclude that the series either converges or diverges. Now let's look at some examples of some alternating theories. Okay, this one, the infinite series of -1 to the n times 3 over n times the natural log of n. N ranges from n equals 2 to infinity. So it's pretty clear that the term 3 over n plus 1 times the natural log of n plus 1. Isn't it pretty clear that that's less than the previous term, 3 over n times the natural log of n. So why is that obvious? Yeah, the larger if the numerator stays the same, the larger the denominator, the smaller the number, right? So n plus 1 is larger than n, and the natural log of n plus 1 is larger than the natural log of n. So this denominator is bigger than this one, so this number is less than this number. So the sequence of positive terms is decreasing. So this is condition 1 of the alternating series test. So this one is satisfied. The second condition, well, if we compute the limit as n approaches infinity of the sequence 3 over n times the natural log of n, the denominator approaches infinity, and so the number approaches 0. So both conditions of the alternating series test are satisfied. So we conclude that this series converges by the alternating series test. Okay, that was pretty easy. Let's try the next one. Here's another alternating series. Okay, it's alternating, -1 to the n plus 1, and multiplied by the natural log of n plus 1 over n. So here's the question: is the term the natural log of n plus 1 or n plus 2 divided by n plus 1, is that less than the natural log of n plus 1 over n? Well, maybe you're different, but it's not as obvious to me that that's the case. So we can use calculus to help us out. If we consider the function f of x equals the natural log of x plus 1 divided by x, if we can show that the derivative of this function is always negative after a certain point, then we can conclude that this function is decreasing. Right? If the derivative of a function is negative on an interval, it means that the function is decreasing on that interval. So this is what we want to do. Is f prime of x less than 0? Say from some point, say from x equals n to x equals infinity. This is not really a true equation, but you get what I mean. Okay, well, just take the derivative. We'll apply the quotient rule. The derivative of the natural log of x plus 1 is 1 over x plus 1. So we multiply the derivative of the numerator by the denominator, then subtract what we have in the numerator by the we multiply that by the derivative of the denominator, and then we square the denominator. So 1 over x plus 1 times x, we write that as x over x plus 1 minus the natural log of x plus 1. And for x greater than 0, the denominator is always positive because it's x squared. So I think we're just about have this figured out. This derivative will be less than 0 or negative when x over x plus 1 is less than the natural log of x plus 1. But what can you say about x divided by x plus 1 for values of x greater than 0? X over x plus 1 is always less than 1. So as soon as the natural log of x plus 1 is at least 1, then we know that it's greater than x over x plus 1, and the derivative will be negative at that point. So if we just allow this to be 1, and then solve this inequality, 1 is less than the natural log of x plus 1, when e to the first is less than x plus 1, or e to the first minus 1 is less than x. So as long as x is greater than e to the first minus 1, or 1.7, the derivative is negative. See what I mean? That's what we wanted to find out. The derivative is negative if x is greater than or equal to 2. So that means the sequence from this infinite series is decreasing. So 1, this sequence, natural log of n plus 1 over n, is decreasing. That's what we wanted to show. Okay, then the second step, now we want to know if the limit of this is equal to 0. The limit as n approaches infinity of the natural log of n plus 1 over n. So what do you think?
Yes, it goes to 0.
Let's see. I forgot. I don't remember. I did this problem. I just don't remember what the answer is. But this reminds us of something from Calc 1. Maybe if I get another piece of paper. So if we have f of x equals the natural log of x plus 1 over x, and if we compute the limit of this as x approaches infinity, we get an indeterminate form. The natural log function goes to infinity as x goes to infinity. So we use L'Hopital's rule, right? Maybe you already did that. Okay, so the L'Hopital's rule, we take the derivative of the function in the numerator, which is 1 over x plus 1. The derivative of the denominator is 1. And this limit goes to 0. Yep. So we apply that to our limit of the natural log of n plus 1 over n, and this goes to 0. Okay, so that tells us that this alternating series converges. Both of the conditions of the alternating series test were satisfied. So the alternating series converges. So I'll make a note, converges. Okay, the next one, we have the infinite alternating series. The terms are -1 to the n minus 1 times 1 over n. So the first few terms, 1 minus 1/2 plus 1/3 minus 1/4, and so on. So this one's pretty obvious. So 1 over n is what is that compared to 1 over n plus 1? Yeah, 1 over n is greater than 1 over n plus 1. So the sequence is decreasing. So 1 over n is decreasing. As n approaches infinity. And then in the second condition, the limit as n approaches infinity of 1 over n, we know that goes to 0. So both conditions of the alternating series test are satisfied. So the series converges. Okay, notice that this alternating series, well, if you took out the -1 to the n minus 1, and if we just had the terms 1 over n, you would recognize it as the harmonic series. So this is called the alternating harmonic series. So the harmonic series is a famous one, and the alternating one is sort of famous. So this one, the alternating harmonic series converges to a famous number. So keep that in mind and see if you can figure it out. If not, I'll tell you at some point. Well, we have a couple of minutes left. We can at least get started on this next one. We have another alternating series. So notice that the terms 2 to the 2n minus 1 over 4 to the n. Well, we can rewrite this so that it's perhaps easier to work with. The only thing that looks a little out of place is 2 to the 2n. 2 to the 2n is perfectly fine, but what's another way to express 2 to the 2n? Using properties of exponents, 2 to the 2n is 2 to the second to the n. 2 to the second is 4, so we get 4 to the n minus 1 over 4 to the n. So if we just consider the second condition of the alternating series test and compute the limit of this, 4 to the n minus 1 over 4 to the n, what's the limit of that? Here we have a few seconds. We can use the technique, we multiply that expression by 1 in the form 1 over 4 to the n divided by 1 over 4 to the n, or equivalently, divide every term in the numerator by 4 to the n, divide the denominator by 4 to the n, and we get the limit of, as n approaches infinity, of 1 minus 1 over 4 to the n over 1. This limit is equal to 1. Okay, so that just tells us that the alternating series test fails, but we can't conclude by that it's divergent. But what we can use is the divergence test. So it's too bad we're out of time. If we use the divergence test, we have to take the limit of the terms from that sequence, which includes the -1 to the n plus 1. We'll finish this one on Friday, but maybe you can work on that limit and use the divergence test on that one. Okay, that's all for today.